Hello guys, welcome to the physics lesson. In today's lesson, we'll be looking at vectors and scalars. We were supposed to be looking at measurement of time. Now looking at the work which is involved for me to prepare that lesson. I've seen that first of all, let me do vectors. Then after I've done vectors, then I will be making a lesson on measurement of time. Alright, so let's look at vectors, and first of all, the first thing that we'll do is to look at their definition. Definitions are very important. If you usually go through past papers, you would come across questions where they would ask you to define vectors and scalar quantities. So what are vectors? So let's start with vector quantity. So we are saying a vector quantity is that quantity which has both magnitude and the direction. So any quantity that has a size, which is magnitude. Magnitude here means size. So a quantity which has both size and direction. A quantity which has both magnitude and then it has direction. That quantity, we call it a vector quantity. That's what you should do. No. Then magnitude is the size, as I've explained. So this magnitude here, magnitude is actually size. Then direction is direction, the way we know. So quantities that have got both magnitude and direction are referred to be vectors. Now let's look at just the examples of these vectors. So let's look at examples. So examples include, we have a quantity like velocity is an example of a vector quantity. A quantity like momentum is an example of a vector quantity. And then we have force as an example of a vector quantity. Displacement, it is an example of a vector quantity. Then acceleration, then also weight, then impulse, etc. So these quantities, why they are called, why they are examples of vector quantities, these quantities here, is because whenever you are explaining or describing them, you need to talk of the size and also the direction. For example, velocity is the rate of displacement in a specific direction, or the rate of change of distance moved in a specific direction. So it means that it is more like speed, but whenever you are talking of velocity, you need to talk about direction. Let's say you see a car passing by, moving at a particular speed. If you say you saw a car moving at 80 kilometers per hour, that is just speed. But if you say I saw a car moving at 80 kilometers per hour moving in the eastern direction, then you are describing velocity, meaning you have included the quantity of the speed, which is 80 kilometers per hour. Then you have also included the direction in which the vehicle was going, in the eastern direction. Then momentum as well is like a force, okay, times the speed, or mass times speed, something like that. Then momentum as well requires direction and also magnitude, as well as force. Examples of force: force always acts in a certain direction, okay? So it is also a vector quantity. Displacement, which is a change of a position. Well, that's what displacement is. If you were at one position, then you move to another position, you have been displaced, okay? You have moved from one place to another. That is displacement. So that displacement is also a vector quantity, because you can tell your friend that when I stood at this point, I had to move in the east direction, or west direction, or south direction, or north direction. So when you are describing like that, then that is a displacement, and it has magnitude, and then it has direction. Because if you say I moved at 10 meters in the eastern direction, that is already 10 meters is already magnitude or size of your movement. Then the eastern direction is actually a direction already, okay? So also acceleration and weight, impulse. So this is how these things work. Then let's look at scalar quantity. So it is a quantity which has magnitude only. So a quantity which has magnitude only is referred to as a scalar quantity, meaning that whenever you are describing a scalar quantity, you just need to talk about the magnitude and you do not need to talk about the direction. So scalar quantity is a quantity which has magnitude only, or you can say it's a quantity which has magnitude but no direction. That also is the definition of a scalar quantity. So with a scalar quantity, you only deal with what? With the magnitude alone. You don't need to talk about direction, nothing about that. Okay, so let's continue. Let's look at examples of a scalar quantity. So examples of scalar quantities include the temperature, then we have volume, then we have mass, we have distance, we have speed, we have energy, we have power, we have charge, we have density, etc. Meaning that for example, if you are reading the temperature of the body, you put a thermometer, then you find that the temperature is 26 degrees Celsius, okay, or let's say 30 degrees Celsius. That is the temperature of the body. Do you need to talk about the direction? Does temperature has direction? Nothing. You can't say the temperature of the body is 30 degrees due east, or in the east direction, or in the west direction. That will not make sense, because temperature, when talking about it, you need just to read the magnitude, which is the size. You say 30 degrees Celsius is the temperature of the body. That's all. Also volume. If you say the volume of the water in the beaker is maybe 20 milliliters, do you need to state direction to say, oh, the volume is going in this direction? Does it move? No. So what about mass? Mass also nothing. If you go on a scale, you stand and find that your mass is 65 kg. Do you need to say my mass is 65 kg due east, or in the southern direction, or northern direction, or western direction? Nothing. You need just to talk about the mass. That's all. You don't need to talk about the direction, because it doesn't make sense. Even the distance, if you are talking about distance between 2 points, so say, okay, the distance between Kalomo and Sesheke, it is maybe 50 kilometers. You don't need to talk about direction when you are giving distance. Also speed, if you just say, oh yeah, the speedometer at which the car is moving is 40 kilometers per hour, you haven't even mentioned the direction, then that is just speed. It's a scalar quantity, it's not a vector. Also energy, the energy that something has, your energy in your muscles, doesn't need direction. Okay, then also power, the rate of doing work, also doesn't need direction. Charge also doesn't need a direction. These are the fundamental properties of matter. Then density as well doesn't need direction. So these are examples of scalar quantities, a quantity which has a magnitude only. Now let's look at addition of vectors. So we are going to look at addition of vectors. Very important that we look at addition of vectors. So what you must understand is that several vectors can be added to get one resultant vector. So if you have several vectors, you have so many vectors that are acting on one point. You have several vectors acting on one point. Those several vectors, you can do what? You can add them. Okay, can be added, and so that when you add those, you get one vector. That one vector which you are going to get is the one we call the what? The resultant vector. That's what we call that one vector which you get is what we call the resultant vector. Okay, very important you know these terms, because mostly I see students or learners or GCE candidates or even internal candidates, they find it hard to answer questions on vectors because they don't memorize terminologies or the terms like this term we are using here. Okay, so now let's talk about this further. So we are saying the vectors which are added are called components. Yeah, so those vectors which get added are called components of the resultant vectors. So the smaller vectors which you add to get the resultant vector here Those smaller vectors which you add are the one we call the component. It's very important you understand this. Okay, so we are saying when adding vectors, the magnitude and the direction of the components has to be taken into consideration. Okay, when you are adding vectors, so the direction and magnitude has to be taken into consideration. Okay, if you are adding the vectors, you need to know the direction in which the vector is going, and then you have to keep that direction. You don't need to change, and then you have to maintain the magnitude or size. So it's very important that you know adding vectors involves you maintaining the magnitude and also the direction. Very important, these things. Then we are saying that a vector quantity can be represented by a directed line segment whose length is proportional to the magnitude, and the arrow head on the line shows the direction. So what we are trying to say here is that a vector quantity can be represented by a directed line segment, meaning if I want to talk about a vector quantity like displacement, sometimes I can represent it using an arrow like that. Okay, that's what I can use. Okay, let me just change this one into a different color. I think let me just use, which color can I use? Black, because I'm already using black here. Okay, so let me just use black. So you can represent it by an arrow, which is a line segment with an arrow. So this from here, this is what we are calling the line segment. Then this part here, it's what we are calling the arrow. So a vector quantity must have these things here. Okay, so it must have these things here. It can be represented by a line segment like this. Now what we are saying is that a vector quantity can be represented by a directed line segment. So this is a directed line segment, meaning that this line segment we have here, it has magnitude and direction where it is facing, like it is facing in the east. So we are saying whose length is proportional. So this length from here up to here is proportional to the magnitude, so is equal to the size. So if I have another vector here, I draw it like this, facing in the same direction. So these two vectors here are not the same. This longer vector here is bigger than this first vector, shorter vector here, because the size of the length is equal to the magnitude. The larger the longer the length, the larger the magnitude, and the shorter the length, the smaller the magnitude. Okay, and the arrow head on the line shows the direction. So these arrows, they're showing direction, like this vector is moving from this direction going into that direction. Okay, so like it is moving from, we can say this is west direction, that's where it is moving from, and then it is going where it is going into the, we can say it is going into the east direction. So this is what it shows. So this is where it is coming from. This part is called the tail, meaning that is where it is coming from, and this part, it's called the head, that's where it is going to. So that is what you must know here. That's what we mean here, guys. Okay, so yeah, so very important that you understand these are things that we are talking about here. Okay, so let's move. So now we are going to say, suppose we are given vectors A and B are shown below, find their resultant. Okay, so we have vectors. Let's say we have this vector here. Okay, this is the vector A, and then we have another vector B here. So they can ask us to find their resultant. Remember, their resultant is the addition. You add this vector and this vector. Now, how do we add vectors? It's very important you understand. We have method 1. we use what we call head to tail method. So what is head to tail method? So here, under head to tail method, you join the head of the first vector to the tail of the second vector. Meaning that if this is the first vector, right? So we get this tail here, you put here like that. That's what we do. So we are saying the resultant is from the tail of the first vector to the head of the second vector. You will understand this. Let's say we pick this as the first. If we want to add this, it's better we get this one, we put it here. The way it is facing this way, that is how we are going to maintain. We'll pick this vector, put it here, and just push it. This tail comes and touches there. Okay? Then we are adding. Now we are saying the resultant. Remember, when you are adding two vectors, the aim is to find what? To find the resultant, which is that one vector we talked about earlier on. So if that is the one you are aiming at, so in this case, we have added by using head to tail method, where we have gotten the tail, putting it at the head. Then for us to find the resultant, we are told the resultant is from the tail of the first vector, from the tail of the first vector, like from the tail of the first vector to the head, okay, to the head of the second vector. Okay, that's what we mean here. Okay, so from the head to the tail. So meaning that it is going to be in this way. We'll draw a line from here to there. So this one is going to be called the resultant. So that is what is going to be the vector. Okay, so this will be the resultant, and it will be the answer of adding this vector and this vector. It will be FR. FR stands for resultant force or resultant vector. Now we can also do it the other way around. We get this one, we get the vector B as it is, then we get this vector, we put it at the tail. The way it is, we lift it, we put here, I'm putting it here, we put it the way it is. So we get the way it is, you get this tail, you put it at the head here. Then you draw from the tail to the head a line there like that. So that line, also this one will represent the resultant vector. So this is the resultant vector that we need to know. Okay, so the second method that we can use is called parallelogram. So to use parallelogram, we are saying join the tails of the two vectors and complete the parallelogram. So you have, let's say, this vector here, right? And then this vector B here. These are the ones. So here they are saying to find the resultant using parallelogram method, you just join the tail. This tail comes here like here. We get this one, I've put this one, then I've picked this vector, I've come to join it here. Then after we join there, we create a parallelogram. We complete a parallelogram by drawing a line here which is parallel to this and same size, and then we draw another line from here up to here, okay, like that, the same size, facing the same direction. Then we are saying the resultant is the diagonal from the tails of the component vectors to the head, in fact. So from the tail to the head. So the resultant, if we use this parallelogram, then the resultant vector that we'll find, it should be the line from the tail to the head here, or to the resultant is the diagonal from tails of the component vectors. So from here up to there, that will be the resultant, in fact, vector here. So the resultant will be this one here. Parallelogram usually works with measurements. So parallelogram, if you are given this vector, maybe they say this is 4 meters, then this one they say it is 6 meters, then they say we are adding these two vectors. So meaning what you need to do, like in what you need to do, if they've told you that this is 4 meters, so you need to use a ruler. Okay, So you need to use a ruler. You measure maybe 4 meters. Another one, if they told you that this is a 5, okay, since 4 meters cannot be put on a paper, so you measure just 4 centimeters here. You reduce that 4 to 4 meters to 4 centimeters. Again, if this one is 6 meters, you reduce 6 meters to 6 centimeters. So you measure another one. You put this side 4 centimeters, then 6 centimeters. Then after you do that, you make a line which goes like this. Okay, again, this one should be 4 centimeters, another one like this, 6 centimeters. When you join these properly using rollers, then you get a line from here. You join a line from here, okay, like from here up to there. After you join, you need to measure this line here using a centimeter rule. Whatever value you are going to find when you measure, that value is going to represent the resultant. That will be the resultant. So this is how these things work here. Okay, now let's talk about how we can prove that the parallelogram is correct. We can prove it using what we call Pythagoras theorem. So imagine in Pythagoras theorem, imagine we have a vector A which is facing in the northern direction and a vector B which is facing in the eastern direction, and these vectors are at right angles to each other and they are joined. You see that they are joined tail to tail as though we are using parallelogram. So if they are joined tail to tail, meaning we can complete also this one here and also this part here we join. Then the vector magnitude of these, it will be from here to there, and this will be the resultant, a vector. It will be from here to there, okay, which can be represented by C. Now we can prove that it can be C using Pythagoras theorem. So this becomes like a rectangle, but if we pick this portion here and this portion, this one can represent A here. So we can say like A, this is the size of B, this is the size of A, because from here up to here it is A, so here it is A. So we, according to Pythagoras theorem, we can find the magnitude of this just by calculation, where we can say C as a resultant magnitude can be found by saying A squared plus B squared. Okay, then you square root this. That's what can be found using Pythagoras theorem. So how can it be? Like I already said, if you can measure from here up to here and then measure from here up to here and ensure that from here up to here it's the same as from here up to here, and then from here up to here it's the same, then if you measure from here up to here, the value that you are going to find, it is going to be the magnitude. And if you use Pythagoras theorem to prove that value using just calculations, it will be correct. Okay, so let's say for instance this value here is 30 meters and then this value here is 40 meters. Okay, then using Pythagoras theorem, we can say that we can use this. We can say 30 squared plus 40 squared using that formula I've shown you. Then we can square root this, then we can say equals C is equal to, then 30 squared is 900 plus 40 squared is 1600. Then you square this. Then if you add this plus this, it will be 2500. Then you square root 2500. Let me just get a calculator because most of people do not know how to use calculators. So let me do this. Let me reduce my calculator. Seems to be too big. It's not fitting the size of the screen that I'm using. Okay, it has reduced to fit the size. Yeah, so let's say we have 30. How did we find that? We said 30, there's a square here. You have seen it is 900. Okay, then 40, there's a square there which is 1600. So if we were to add this 900 plus this one here 1600. What are we getting? We are getting 2500. Now let's square root this. So let's do like this. Let's write square root. Have you seen square root? According to my calculator, it is bringing that one. Yours might be different. So say square root of 2500. It is going to be what? 50. So that's what it is going to be, 50. So here C is going to be 50 meters. So from here to here to be 50 meters according to Pythagoras. But if you measured in reality as well, provided you measured from here to here, it's the same from here up to there, then at right angle as well, then from here to here, it is also 40, again at right angle to each other. Then when you join this line from here up to here, if you measure it, then it is also going to be 50 meters. Okay, that's just the proof of a parallelogram using Pythagoras theorem. All right, so let's proceed and look at adding vectors in the same direction. So we can have vectors acting on an object in the same direction. Okay, so if the vectors are acting in the same direction, find algebraic sum of the vectors. Okay, so let's say we have an object here where we have one vector we are calling vector 1. In this case, vectors, we already said the examples of vectors are forces. So let's say we have a force as a vector acting in this direction, force 1, another one, force 2, acting in the same direction. Now we still have another one like this one acting in the same direction, vector 3 or force 3. We are saying if two or more forces, which are vectors in this case, are in the same direction, you see they are pointing in the same direction, east, east, east. The resultant vector is found by adding all the individual vectors. Like I've already said, find algebraic sum of the vectors. So the addition of this vector, this vector, this vector will give us what we call the resultant vector. Okay, so the resultant vector is going to be found by just adding these individual vectors. So we can have that resultant vector, which in this case we can represent by FR, which is the resultant force. It is going to be the addition of this one and plus this one plus that one. Okay, this. Okay, so sorry, so this one is supposed to be F1 here. I just didn't change, so let me try if I can just put one there. So let's just say this is F1. Okay, except that it's not agreeing, but you can change it. Try to change that one as F1. Okay, so now let's look at an example. So this is F1. You need to indicate F1. So let's look at an example here. Let's say in reality now we have been given here we have 60 Newton acting this way, and here we have 20 Newton acting that direction on this point, and then we have 40 Newton acting at this point. Then we are asked to find the force, the resultant force. So the resultant force will be, since they are all facing in the same direction, add them. We start with 20 plus 40 plus 60. Then if you add these 40 plus 20 plus 40, which will give you 60 plus 60, 120. So if you add these, you have 120. Okay, why? Because they're facing in the same direction, so you add them just the way we add numbers. Now let's look at a situation where we have vectors in the opposite direction. So we are saying if the vectors are in the opposite direction, find the difference, and the resultant is the direction of the larger force. Meaning that if you have two vectors that are acting in the opposite direction, one is acting in the east, it is facing west, I mean, which is F1. Let's say another one is facing in the east, and F2. So we are saying if the same force acts in opposite direction, their resultant vector is 0. Okay, so if these were the same forces, here maybe 40 Newton, 40 Newton, then it will be 0. And we are saying if we have an equal and opposite forces, their resultant vector is found by subtracting the smaller vector from the larger vector. So in this case, between vector F2 and vector F1, the one which is bigger is F2, because even the length, remember, length is equal to the size or magnitude of the vector. So in vectors, when we make a line longer, it means that vector is larger than the other. This one shorter, it is smaller. So according to this rule, these vectors are not the same. If they were the same, then the magnitude or the resultant vector would be 0. Now, since they are not the same, they are acting in opposite direction, meaning that their magnitude will be different, but it will be found by getting the subtraction of the smaller vector from the larger vector. That's what we are saying here. So the formula would be like the resultant vector FR, resultant force, it is going to be the larger vector, which is F2, minus the smaller vector, which is F1. Now, the direction of the resultant is in the direction of the larger vector. So the resultant now, is it going to face this direction or that direction? It will be that direction, the direction of the larger force here. So that's where the resultant will face. Okay, so that is that. So let's say in reality we have now a vector here which is 30, and here we have 50. So if we were to find now the resultant here, it would be equal to F, which is the larger one, 50, minus the smaller one, 30. Then we'll say 50 minus 30, which will be 20 Newton. So this one, it is going to be 20 Newton facing in the east direction. Okay, so that is that. Now let's assume we have equal vectors. This vector, you see the line is the same size as this one, meaning they're equal. So let's say this one is 30 and this one is 30. We said if the same forces acts in opposite direction, they're the same. This is 30, this is 30, but they're opposite. This one is west, this one is east. Their resultant vector is 0, meaning you must subtract each other and get 0. So this formula can still work. You see that it will give us 0. You get, let's say, this one, which is 30, minus this one is still 30. So you'll find that the resultant vector will be 0. 30 Newton minus 30 Newton, it will be 0 Newton. Yeah. So that is how these things are going to be. Now, to avoid the lesson being long, I decided to end the lesson here so that we shall continue from the next lesson, where we'll be looking at other types of vectors. Okay, for now we end here, and bye. See you in the next lesson. This has been your teacher, the DMS online school teacher, Mr. Masumba. Bye.